Hi, welcome back. I'm going to introduce the idea of work, and this is work in the physics sense, not in the everyday go to work, do your homework, that kind of work. Physics work is a lot different, has the same root, but it means something very specific. So let's go ahead and get started. If you notice, we have an object up here, this little green ball. We're applying a force to it. And our object is going to move through this displacement of r. And during the time that it's moving, this force is doing work. The only part of the force that's doing work, however, is the part that is lies along the displacement in the direction of r. So if we go back to vectors, that would be the x component of the force. And the x component, if you remember, goes along with cosine. So that's just a little bit of information of how this formula works. It's really not a vector. It's a mathematical operation called a dot product or a scalar product. When you multiply two vectors together, there's two ways of doing it. This is the first way. We'll learn about the other way at a later time. And in a dot product, what it's saying is that it's the projection of the force vector onto the displacement vector, which is a fancy way of saying if you had a big flashlight shining down from above, where would the shadow of the force vector be, or how long would the shadow of the force vector be on the surface that r lies in? So that's what this projection thing means. Now, so work is what happens when you apply a force or a combination of forces to an object over a distance. And what that does is it changes the energy, the amount of energy that the object or the system has. And that's what work is. Now, what's energy? Well, energy is the ability to do work. It's a very circular argument, but that's what we have. What's nice is work is a bridge between forces, which are vectors, and energy, which are scalars. As we know, dealing with vectors can be really tedious, dealing with all the components, and basically have to doing three problems to get a single answer. You have to do an x problem, y problem, and then you have to put it all back together to get the answer to the overall problem. Well, once we work in energy, we don't have to do that. We don't have to worry about whether it's going north, south, east, west, or anything like that. So the formula is work is equal to the force times the displacement times the cosine of the angle between the force and the displacement. Now, the displacement, the symbol is r, and that's because we're working in multiple dimensions, 3 dimensions possibly, most likely just 2. And we use that r to symbolize displacement. We get away from the x's and the y's because those are just a little bit too specific. Okay, next in the journey is what are the units of work? Well, forces times distances. Forces are measured in newtons, distances are measured in meters. Multiply those two together, newtons times meters. Well, we give that a special name called the joule. It's named after James Joule, one of the early pioneers of work and energy. So 1 joule is the amount of work done moving a body 1 meter when you apply 1 newton of force to make that motion happen. Now, there are other unit systems that are very common in the field of energy. We won't use them. We're going to stick with SI units. But in the British system, the foot-pounds, that's still very common in our world. Energy, manufacturing, cars, engineering. The CGS system, not so much. That's the centimeter gram second system. At the atomic level, for very small things like electrons and protons, we use an energy unit called the electron volt. What that does is it gets rid of a whole bunch of decimal places. It gets rid of 19 decimal places. We don't have to deal with really, really small numbers. We get to deal with more human-friendly numbers in that case. It's used mostly for us in the electricity world, but if you were to go on to do particle physics, anything like that, you would work in the terms of electron volts. Energy, some of the concepts here. Body experiences a change in energy when one or more forces do work on it. And that body must move under the influence of that force or forces to say that work was done. If the force and the displacement of the object are in the same direction, or some parts of them are in the same direction, at least partially aligned, we call that positive work. And the maximum positive work is when the force is in the exact same direction as the motion. If the force doesn't cause any displacement, for example, pushing against an immovable wall, you may be getting really tired and applying a big force, but if the wall doesn't move, you've done no work. Now, forces can do negative work. If the force is applied opposite the direction of motion, then the work is negative. That's commonly done like if you're slowing a car down, you're catching a ball, the force is applied in the direction opposite of the motion, you've done negative work. It's not always a bad thing. Negative work is really important, especially if you're driving your car. You want to be able to slow it down. You want those brakes to do negative work on your wheels. Very important. To recap, and some examples here. No work done if it causes no displacement. Forces can do positive, negative, or zero work. For example, when you push a box across the floor, the box has weight. That's perpendicular to the floor. It's a force, but it's doing no work because the box is moving horizontally and gravity is pulling it vertically. No work. The normal force, similarly, the normal force is perpendicular to the floor, which is, the floor is the direction of motion, the horizontal. Normal force does no work. Your push, you're pushing the box is moving in the direction you're pushing, you are doing positive work. Our nemesis, friction. Friction is pushing back on the box, not letting it move as fast as your push would make it move if it was on a frictionless surface. That friction, and it's specifically kinetic friction, sliding friction, kinetic friction does negative work. It always opposes the direction of motion. It's always in the direction opposite of the motion. Static friction, however, is a little bit different. In your car, the static friction between the road and your tires, the friction is pushing forward, is pushing in the direction of motion of the car. In this case, static friction does positive work. Very important to understand the difference between what kinetic friction is doing and what static friction is doing. Here's an example. A man's holding a 50-kilogram box, that's about 110 pounds, at arm's length for 2 hours as he stands still. Is the box moving? No. No displacement, no work. Is the man applying a force? You betcha. You would be really tired after 2 hours holding up a 110-pound box. Okay? Even though he gets tired and he's sweating and he's consuming calories, that energy transfer is internal to his body and has nothing to do with changing the energy of the box. Next up, here's a guy, he's walking across, looks like a dune or a beach. He's walking forward, he's going to walk straight forward 1 kilometer. How much work does he do on the box? Well, he's applying a force to the box, but the force that he's applying is directed vertically. All he's doing is holding the box. We're going to ignore that little fraction of a second when he applies a force to get the box moving forward. Once it's moving forward, He's applying no forces in the forward direction. He's merely holding the box up. His direction is horizontal. The direction of motion of the box is horizontal. The direction of his force on the box is up. Up and horizontal are separated by 90 degrees. There's no motion in the direction of the force. He's doing no work. Doesn't seem right, but that's what it is. Finally, somebody's doing some work around here. This man is lifting a 50-kilogram box 2 meters. How much work does he do on the box? We're going to use our friend, the free body diagram, and Newton's laws, equations of motion, to help us solve this problem. We're not done with free body diagrams. We won't be done with free body diagrams. They're a very important tool. I know many of you would like to leave that idea behind. Okay, so here's our free body diagram, and there's the arrow that's signifying the weight, which is mg, mass times the acceleration due to gravity. And then the man is applying a force upward. And really that's a normal force. You could also call it an applied force. I think I'll go with just calling it F. So how much of a force does a man have to apply to lift the box? Okay, well, let's use our second law, equation of motion. Sum our forces. And we're going to make the assumption that he's not accelerating the box. We're going to say he's going to do it the easiest way possible, and that's to lift it at a constant velocity. So mass is the mass of the box, 50 kilograms. The acceleration is 0. ma is equal to 0, which is equal to the force up minus the weight, which is down. It's minus because it's down, which tells us that the force that the man applies is equal to the weight of the box, mg. Now, going back to the equation for work. Work is equal to force times displacement times the cosine of the angle between the force and the displacement. Well, what's the direction of the displacement? In this case, the direction of the displacement is up. The man is lifting the box up, so the displacement is up. Well, the direction of motion is up, the force is up, the angle between up and up is 0. So we can put a 0 degrees into our cosine, and if you remember, that's equal to 1. The force is m times g, which is 50 times 9.8 for g, times the displacement, which is 2. So 50 times 9.8 times 2. 50 times 9.8 is 490 times 2 is 980. And I probably should fix this here. It's not just multiplying by 0 degrees. It is cosine of 0 degrees. So let's get that in there right. And if you remember, cosine of 0 degrees is times 1. So the work done by the man is equal to 980 joules. Next up is your multiple choice question. Welcome back. I hope that wasn't too hard. Let's do another example. This is very similar to the man lifting the box. The aspect of this problem that's difficult or a little bit more challenging is the units that I gave you. Remember, we have to work in SI units. And while these are SI units, there are prefixes here that are not standard. So we're going to have to do some unit conversions. So let's go ahead and get started on this. Like always, I'm going to start out by drawing a free body diagram. So here's my water drop. And the forces applied to the water drop are its weight, which is mg, and the air resistance. And usually we signify that with the symbol d or F sub d, which stands for drag, air resistance. Now, write the equation of motion. Going to notice right there that it says at constant speed. That tells me my acceleration is 0. Sum of the forces acting on the water drop is equal to 0, which is equal to the drag minus the weight, mg. So that tells us that the drag is equal to mg. Now, going back to work. Work is equal to the force times the displacement that the force is applied over, and then times the cosine of the angle between the displacement and the force. Okay, so let's go ahead and start substituting in our numbers into our equation. Well, the force, if we're doing the work done by gravity, the force of gravity is equal to m times g. Well, our mass is 50 milligrams. Well, milligrams is 10 to the minus 3 grams. And we need to turn that into kilograms, which is 10 to the 3 grams. Well, if you see, there's a 10 to the 6th difference. A milligram is 10 to the 6th times smaller than the kilogram. So that would mean that we have 50 times 10 to the minus 6th kilograms times 9.8 meters per second squared times the displacement, which is 1 kilometer. Again, we have to convert that into meters. This one is pretty easy. It's just 1,000 meters. And times the cosine of the angle between the displacement and the force. Well, the water drop is falling. Displacement is down. Okay, so gravity is down, displacement is down, the angle is 0 degrees, which means that the cosine of that angle is 1. So I'm just going to leave my equation the way it is. 50 times 10 to the minus 6th times 9.8 is 490 times 10 to the minus 6 times 1,000. Okay, so that will be 0.49 joules. 0.49 joules. Now, what work does air resistance do? Well, the force applied by air resistance is the same as gravity. The distance or the displacement is still the same. The only difference is the air resistance is up, the displacement is down, the angle between up and down is 180 degrees, which, if you remember, the cosine of 180 degrees is -1, which means that the work done by drag is a negative 0.49 joules. So that wasn't too bad. Like I say, the equation was pretty easy. The work is just straight up what is the work done. The problem is that you had to do the unit conversions. That's just really a reminder that you have to pay attention to what units are being used. Next is another example problem. We have a father pulling his child in a little red wagon with a constant speed. If the father pulls with a force of 16 newtons for 10 meters, and the handle of the wagon is inclined at an angle of 60 degrees above the horizontal, how much work does the father do on the wagon? Well, free body diagram time. We have the weight of the child in the wagon, m times g. We have the normal force from the ground. We have the force applied by the father, which is 16 newtons, and it's at an angle of 60 degrees. And then there's also some friction force. Well, we're only interested in the work done by the father. Well, the father is applying a force of 16 newtons. Okay, we don't have to worry about our normal or our weight or our friction force in this case, because we're not interested in the work done by those. So the work done by the father is equal to the force applied by the father times the displacement that force is applied over times the cosine of the angle between the force and the displacement. Well, in this case, the displacement is horizontal, and the angle between horizontal and the force is 60 degrees. So let's go ahead and substitute in. The force is 16 newtons times the displacement of 10 meters times the cosine of 60 degrees. 16 times 10 is 160 times the cosine of 60. Well, if you remember, and I'm doing this in my head, cosine of 60 is 1/2, so 160 times 1/2 is 80 joules. So the father does 80 joules of work pulling the child in the wagon over a distance of 10 meters. Let's see what's next. It's your free response. Good luck. We'll see you next time.